Okay, so let's have a look at question 4. So figure 6 shows a water distiller which is used to purify water. The distiller boils water and then condenses most of the water vapor back to water. The water distiller is filled with 5 kilograms of water at 20 degrees Celsius. The specific heat capacity of water is 4,200 joules per kilogram degrees Celsius. Calculate the energy needed to raise the temperature of the water to 100 degrees Celsius. Write down any equations you use. So you're going to have to remember this equation. It's not on the equation sheet. The equation is specific heat capacity is equal to... You can actually get the formula. This is a really useful tip, actually. Specific heat capacity of the water is that, but look at the units. Joules, kilogram, degrees Celsius. Joules divided by kilograms and degrees Celsius. So it would be energy divided by mass and temperature. It's actually the change in temperature. So that's the formula, right? We've got to rearrange that for energy. Okay? Now, like I've said many times in these videos, I would do this like this, multiply both sides by mass and change in temperature. Mass and change in temperature, and then that would cancel there, and I'm left with energy equals specific heat capacity times change in temperature times mass. If you're not confident with rearranging an equation like that, then you can try putting it into a triangle, a formula triangle. This is a bit of a funny one, but the multiplication here means you can treat these like one term. So stick it in the triangle, put energy on top because it's on top of the equation. Whatever's left over, put down here, SHC times M times delta T. Let's make that a bit bigger. Energy on top, SHC here times mass times delta T, and then you think, well, I'm working out what energy, cover energy, you're left with specific heat capacity times mass times change in temperature. So energy equals specific heat capacity times mass times delta T. Sub numbers in. Specific heat capacity 4200 times the mass 5 kilograms of water times the change in temperature. Water at 20 goes to 100, so the change, I'll put it here, delta T equals 100 minus 20 equals 80 degrees Celsius. So 80. Okay. Calculator. Sick of saying it, but bring them to the exams. Practice with your own calculator, not the school's one, otherwise you will fail your exams. Okay, so I get a very large number for the value, but I can't see any mistakes. So, plus it takes a lot of energy to heat water. It's in joules. It's given me the unit, so I don't need to worry about units. 168, and then 4 zeros. 0, 1, 2, 3. Okay, I could have written 1,680 kilojoules, but I'll leave it as joules. Okay, next part of the question. Figure 7 shows how the temperature of water in the distiller changes with time. Energy is transferred to the water at a constant rate. Explain why the graph is a different shape in part A and part B. So what we can see here is temperature rising steadily here, and then it stops rising at B. Okay, so energy being supplied at the beginning, energy supplied at A is raising the temperature and therefore average kinetic energy of particles. Right? So as you're heating up, particles are starting to move around faster and faster and faster. Whatever state it's in liquid state, I think. Right? So in anything, when you're heating it, or any material, the particles have got kinetic energy as they're moving around, but they've also got, depending on how they are arranged, if they're in a solid, for instance, they're vibrating about fixed positions. Well, two particles in a solid are actually attracted to each other, held together in place by bonds. So when they're vibrating, they're stretching those bonds, and it's almost like strain energy. There's energy stored in the bonds, and there's energy stored in the kinetic energy. of the particle, and all of that together would be called the internal energy. Well, the sum of the potential energies and kinetic energies of all the particles in the system would be called the internal energy. So when we're supplying energy at A, we're raising the temperature and therefore average kinetic energy of the particles. Okay? So at B, the energy supplied is going into breaking bonds, or is going into changing state. The state of the solid, the state of the material, e.g. so we're going from liquid to gas, so I may as well use the example they've given us, liquid to gas. Okay, I think I've pretty said enough there to get those marks, hopefully 3 marks. We'll check the mark scheme in a second. When the water drops to a low level, the heater automatically switches off. Explain what problem would be caused if the heater did not automatically switch off. Right, well, let's go back and look at the picture. It's basically a kettle, right? It's a kettle with some gubbins on top here. Okay? What would happen if you let your kettle continue boiling even after there was no water left over? So the heater would, why does that keep coming up? The heater would continue heating the kettle, heating the element, heating the device itself, possibly causing damage. Causing damage or a fire hazard. Right. It doesn't seem like enough points to get 3 marks. Okay. Again, we'll come back to the mark scheme and check that one. Right. The distiller is connected to the mains by 3-core cable. The wires are covered by different coloured insulation. What colour is the insulation covering each of the wires? Right. Live wire is brown. Okay, I've got a nice way of remembering that, but it's a little bit rude. But if you touch it, it might make your underpants go brown, right? To be honest, any of the wires in here are dangerous, so it's a bit of a silly analogy. Neutral wire, I can't quite remember, but the earth wire is yellow and green, right? And then that only leaves one colour left, blue. So again, I'll come back and check that. Which statement gives the purpose of the earth wire? Right, well, the earth wire is attached to the casing, and if the casing comes into contact with any live wires, it's got the potential to electrocute you, right? Sitting there waiting to electrocute you. But if you connect the casing to an earth wire, then the thing automatically shorts out, melts the fuse, and disables the device, basically. So it's going to be something to do with that. It's not that. It melts if the current in the circuit is too high. No, you don't want the earth wire melting. It provides a connection to complete the circuit. Well, it does do that, so that's a potential. It stops the casing becoming live. It's that one. That's the one. The heating element has a power of 2.5 kilowatts. The resistance of the heating element is 17 ohms. Calculate the current. Okay, you're not given any equations. So there's a couple of equations we could think about. We've got Ohm's law, V equals IR. We've got, what else have we got? We've got power equals IV. Okay. So, what have I got? I've got the power. I've got the resistance. And I'm asked for the current. But we don't appear to be able to make any of them work. Okay, so where we're going to have to combine 2 formulas together. Right, so I need an equation that has got power, current, and resistance in it. Power, current, and resistance in it. If I take that and I stick it in for V, I will get P equals I times V is equal to IR, so replace that with IR. I get I squared R. P equals I squared R. Now that looks like a winner. So if I use I squared R, P equals I squared R, I can sub the numbers in. 2.5. It's not 2.5 though, is it? It's 2.5 times 10 to the 3. Or it's 2, 5, 1, 2, not 3. Move the decimal place over 3 times because it's killer. Once, twice, 3 times. Okay? So it's 2500 watts. Will be equal to, okay, I squared, I is what I'm looking for, times the resistance, 17 ohms. Okay, so rearranging from there, 2.5 times 10 to the 3 divided by 17 will equal I squared. Okay, so if I calculate that little bit, 2.5 to the power of 3, just to show you how I'm doing this, 2.5 to the power of 3 gives me, divided by 17, gets me 147.058. So 147.058 equals I squared. Square root that, cancels that, gets me I equals. So the square root of this gets me 12.1. 12.1. Right, so no wonder this thing was worth 5 marks. There's a lot of steps and a lot of things you need to be thinking about for that one. There are other arrangements, other ways of subbing Ohm's law into the power equation. So power equals current times voltage, PIV. You can rearrange for I, so I equals V over R, and you can sub in that, and you get P equals, so I'm replacing that with V over R times V, so it becomes V squared over R. That's another arrangement you may end up using, V squared over R or I squared R. These two particular ways of looking at the power equation do come up, as we've just seen. Is that the end of the question? Yes, it is. So that was all out of 17 marks. Okay, I hope you found this useful. Please comment, subscribe, like and share. Thanks for watching.